Okay, today we begin with chapter 5, energy. Energy is a very important in physics. Until now we studied force, and force is relevant to the equation of motion. The Newton's second law of motion is F equals ma. The equation of motion is the second order differential equation for the position of a particle. And if force is applied to an object and proceed with some displacement, we can define work done by the force. And the work done by the force is defined in here. And as a result, if some work is done on an object, it changes its energy. And most important energy is the kinetic energy. We'll find that the kinetic energy changes depending on the work done on a system. And the work, there are two kinds of work. An explicit work is revealed with the momentum of a particle. So kinetic energy is a kind of work. And we shall find that the energy is conserved for the conservative force. And the ability to carry out the work to increase the kinetic energy of a particle is called the potential energy. The kinetic energy and potential energies are most important works in physics. The conservation of energy states that the sum of the kinetic energy and the potential energy is a constant of time. So total time derivative of the total mechanical energy, that is the sum of the kinetic energy and potential energy, should be zero, as long as the force is conservative. Although the equation of motion is integrated out to find the equation of energy, there is some way to find the equation of motion by making use of the energy information. We shall find that the force applied to a particle, as long as it's conservative, the force can be derived from the potential energy by taking the derivative. Explicitly, it should be minus gradient of potential energy. In fact, that information can be applied to reconstruct the derivation of the equation of motion. I mean, the Newton's second law does not derive from anything else from the beginning. However, we can derive the equation of motion from the energy level, so-called Lagrangian, that is the kinetic energy subtracted by the potential energy. In addition, Lagrangian can be integrated out with respect to time to construct action. Hamilton's least action principle states that the equation of motion satisfies the physical path along which a particle follows, and the trajectory of the physical motion can be obtained when we minimize the action. The action is the time integral of Lagrange. Therefore, it is very important to study energy. While the analysis involving force is quite complicated because it has the force has three components, x, y, z components. If we consider this energy is not a vector but a scalar. So analysis with the scalar function is much easier than we deal with the force, explicit force. Okay, so that's the most important point that we have to study: energy. The work done by a force along a path C gives the work that is the integral of f dot dx along the path C. dw, delta w, that is the work during some finite translation, and that is f dot dx. If the force is parallel to the displacement, then the dw is positive. If the force is perpendicular to the displacement, then the work is zero because the scalar product has a factor cosine theta, where theta is the angle between f and dx. If the force is opposite to the displacement, then cosine theta becomes a -1 and the work is negative. For example, if we consider the damping force is opposite to the direction of motion, that means it's proportional to V, but it has a coefficient with negative value. So this is the case for the force is opposite to the displacement. In this case, the work done by this force is always negative. What is the example of this kind of force? That is the magnetic force. Magnetic force on a charged particle moving in the magnetic field is Q, charge Q, multiplied by V cross B, where V is the velocity of the particle and B is the magnetic field. Next, we consider the power. Power is the time rate of doing work. So the differential of work that can be computed by scalar product of force and dx, displacement. We divide by differential of time. Then this is time rate of work, and this is time rate of work. But F For short time, f is should be some constant value, and dx over dt results in the velocity. So power, the time rate of the work, is f dot v. Okay. If you consider the magnetic force on a charged particle moving with velocity in the magnetic field B, the force does some work. If the work done by the force and with the time rate power Fm dot V, and as we have already stated, Fm can be substituted here to find V cross B dot V. This is a triple scalar product, and it should be something like that. Q, epsilon ijk, three vector indices. The first index is I, second index is B, J, and third index is K. As you know, Vi, Vk, they are symmetric under exchange of I and K. And epsilon ijk, I and K, they are antisymmetric under exchange of I and K. Therefore, the multiplication of the symmetric and asymmetric and antisymmetric tensor will give 0. Another way of finding that is V cross B is perpendicular to V, and that is to be made on the scalar product will be made with V. Therefore, the cosine theta equals 0. Next one is kinetic energy. Non-relativistic kinetic energy of a particle is 1/2 m times v squared. You know, velocity can be obtained by dividing the momentum, linear momentum, by mass. Thus, we can substitute in here to find that 1/2 m p over m squared, resulting in p squared over 2m. We can see the kinetic energy is independent of position. Sure, if you do some work on a particle, the kinetic energy may increase, but explicitly, kinetic energy is a function of P, and P is a function of some. P must be a function of. As a result, it can be changed if you do some work. Anyway, the partial derivative with respect to time should vanish. In a similar manner, we can consider the total time derivative of kinetic energy. As you know, this is independent of t. P may be depending on t, but there is no explicit time dependence in this formula, p squared over m. So, if we compute the total time derivative, we make use of chain rule. First, partial time derivative of t, and then there's explicit p dependence appears. So I take the partial derivative with respect to p and take the time derivative of p. And this one vanishes. Time derivative of p is actually force. And what is the partial momentum derivative of t. Because t equals here, 2m is here, and the partial derivative of p squared with respect to p should be 2p. Thus, we have p over m, that is the velocity. So, as a result, kinetic energy, time derivative of kinetic energy is Fv. Sure, if we extend this one into 3 dimensions, we have this kind of result. This one was for the one-dimensional case. In 3-dimensional case, we have 3 derivatives regarding the P1, P2, and P3. And we take the time derivative of Pi. Okay. Therefore, this one is Pi dot, and this one is a Pi over m. As you know, the kinetic energy is 1 over 2m, P1 squared, P2 squared, P3 squared. So, this partial derivatives picks up only the Pi component among 1, 2, 3. So, once I equals 1, then it is 2p1. If I equals 2, then it should be 2p2. And if I equals 3, it should be 2p3. Therefore, this is a Pi over m. Pi over m is velocity over velocity, the ith component of the velocity. Pi dot is the ith component of force. And the sum over I means the force scalar product with the velocity. Right. If I use this expression, partial derivative with respect to I, and Pj sum over j, Pj squared, then by making use of chain rule, we take the derivative with respect to Pj first, then we get 2Pj, and then Pj is here. We take another derivative, a partial derivative, with respect to Pi. So, we have round Pj over Pi. As you know, round xi over round xj vanishes when I is not equal to j. And it is non-zero if they are the same. That is just Kronecker delta. So it is 0 for I is not equals to 0, I is not equal to j, and it's equal to 1 for I is equal to j. Therefore, it is Kronecker delta, delta ij. It is true not only for the Cartesian coordinates, but also for generalized coordinates or curvilinear coordinates. So they should be the same. The indices should be the same to have non-vanishing contribution. Again, round qi over round qj is delta ij. In a similar manner, round pi over round pj, that should be non-vanishing only if I is equal to j, and then non-vanishing value is just 1. Therefore, this is, again, Kronecker delta, delta ij. So we have over factor 1 over 2m and 2pj, and then delta ij. Delta ij kills j and replace this j with I. Therefore, is Pi over m, and final result should be the velocity, ith component of velocity. All right. So we have studied that time derivative of the kinetic energy should be somehow partial time derivative of t and partial momentum derivative of the kinetic energy. And according to chain rule, we have to multiply the time derivative of momentum. And this one, because of formula p squared over 2m does not have an explicit time dependence, this one vanishes, and this one is a force, and this one is the velocity, and sum over I means it's F dot V. Next, we consider the work kinetic energy theorem. We already noticed that the time derivative of kinetic energy is Fv. So, before we go ahead, we review some simple algebra. Differential of a scalar product of two vectors. This scalar product of two vectors can be expressed in terms of components, that is ai, bi. Now we have two functions with differential. Then Leibniz rule can be used to find the differential of a, and we'll multiply the second factor and keep the first factor the same and take the differential for the second factor. Now, still this one is a vector, ith component of differential, and this is ith component of differential dv. Therefore, this one, again, they can be combined as a scalar product. So, what we find is this one is a dA dot b plus a dot dv, right? What happens if b equals a? If b equals a dot b becomes a squared, and this one is a dA dot a and a dot dA. You know, the scalar product is commutative. We can flip the order to have 2 times a dot dA. Therefore, if I take the time derivative, this result is 2a dot time derivative of a. Again, if I divide 1/2, if I multiply 1/2 both sides, then a dot, its time derivative, equals 1/2 time derivative of a squared. Okay, using this one, we can simplify this algebra. Work, differential of work, due to the force that carries the particle with the displacement dx, then, you know, for a short time, a very short period, the velocity can be fixed approximately, but as a differential, it is just constant, and v dot dt, v times dt will be the displacement, infinitesimal displacement. We know F dot v equals F dot momentum divided by mass. F equals time derivative of momentum, and momentum divided by m. We find that over factor 1 over m, p dot dp. P dot dp. But we can make use of this relation. Something dot time derivative. That means 1/2 time derivative of square. So this one can be replaced with 1/2 dp squared. Right? So let's compute the work done by some force from A to B. That is F3 dt, F dot V dt, integration from position A to position B, from time TA to time TB. Okay? Now, if we take the time derivative, then power is work dW over dt. Now, we make use of this result. This is dW. dW is 1 over 2m dp squared and divided by dt. Aha. But you know, p squared over 2m. This 2m can be moved inside the derivative. Inside. This is just constant in the non-relativistic theory. Therefore, this is the time derivative of kinetic energy. This dt is the same. That means differential of work should be the differential of kinetic energy. They are identical. In case we have some finite shift, then this differential, infinitesimal differential, can be integrated. Then we apply this relation. This differential of work should be the differential of kinetic energy. That means kinetic energy at B and subtracted by the kinetic energy at point A. Therefore, the kinetic energy at B should be the same as the kinetic energy of the starting point and work done by the force during the displacement from A to B. We remember this relation. Differential of a scalar product is dA dot B plus A dot dB. What happens to the case of the cross product? Should it be the same? Or B cross dA? Or it's confusing, but actually this is right. Let me check it. First, we can write down component-wise A cross B in the Cartesian coordinate system. In the Cartesian coordinate system, A cross B should be EI hat epsilon ijk AJ BK. And this EI hat and epsilon ijk, what are the differential? The reason why we take the Cartesian coordinate system in this expansion is that there is the differential of, for example, if we make use of spherical coordinate system, E, R, E, theta, and E phi are all non-vanishing if we take the derivative. As you know, if you change the angle, then radial vector becomes, its radial vector has the component, the tangent to the radial vector. Therefore, this kind of derivation should be done. It should be very simple only if we take the constant basis vector case. That is the Cartesian coordinate. So if we make use of Cartesian coordinate, this is a constant vector. So dE I hat equals 0. And epsilon ijk is a number. Delta ij is number. So everything does not have any differential. So we can factor these out of differential. And this total differential for Aj and Bk should be simply computed. This one is copied here, and for fourth piece is the derivative of this. So differential of Aj multiplied by Bk. And next one is keep this Aj the same and take the differential of Bk. Therefore, we have this contribution. Now we find that this is Ijk, Ijk, and this is J is attached to the vector dA, and K is attached to the vector Bk with the same cyclic order. Therefore, the first term gives dA cross B, and second term gives A cross dB. This is the same as what we expected, but be careful. If you change the order, the result will be different. Okay. Next one is conservative force. What is conservative? Force is conservative if this integral is 0. What is this? The circle. This is path, and circle means the path is closed path. The work done by a force along a closed path always 0. All right. A path C is given here. We start from A, arrive at B, and return to the original place. So this is a closed path. This integral should be the work done by the force during this motion. And this is 0. Then we call this conservative. Once the force is conservative, we can define the potential energy. The reason is that if I return to the same position, then work done by the force is 0, so kinetic energy is the same. Kinetic energy is conserved. The work kinetic energy theorem states that this is the amount of work, and that is the same as the difference of the kinetic energy. But if this is vanishing, that means the kinetic energy is conserved. So we define the potential energy to be the negative of the work done from a fixed point. There's a reference, it is called the reference point x0, to a position, to a certain position. And this u0 is the value of the potential energy at the given reference point. The reason why we attach this negative sign is this potential energy, as the name potential means that the energy has, this potential energy has some ability to carry out the work, to change the kinetic energy of a particle. So It is a hidden, but if it is necessary, then it brings out its own energy to change the particle's energy, the particle's explicit energy, that is called the kinetic energy. For example, let us compute the kinetic energy. Let us compute the potential energy of spring force. We have a spring force F equals minus kx. Then we can substitute this one in here. K is a constant, x dot dx, x0, vector x. As you know, this one should be 1/2 dx squared. 1/2 dx squared. So therefore it is u x0 plus 1/2 k x squared subtracted by x0 squared. Sure, we can always choose this reference value for free. So it's better to define u0 is 1/2 kx0 squared. Then this result becomes simple. As you know, this x0 is actually 0, and at that point, the restoring force becomes 0 if we substitute x equals 0. So usually people use the reference point x to be 0 for the restoring force of the spring. Next, we consider the closed path one more time. A closed path, the work done by the conservative force is 0 if we carry out the work along a closed path. Here, what happens to the case if F carries some work along the path C1 and along the path C2, and the starting and ending point, end point of these two paths are common. But you will find that the C2, if we flip this direction, then let me call this one to be minus C2. If I combine these two paths, then it becomes a closed path. So C1 minus C2 should be a closed path. Therefore, conservative force, the work done by the conservative force on a closed path should be 0. But this is integral. This one can be divided into two pieces. The work along the path C1 and the work along the path minus C2. The work done along the path minus C2 should be minus value, negative of the work done along the path C2. Therefore, the work from O to A along C1 and along C2, they must be the same. If they are not the same, then they do not cancel, and it contradicts to the starting point. Therefore, another interesting result is that coming from this fact, conservative force, the work done by a conservative force along a closed path should vanish. That is equivalent to the following statement. Work done by a conservative force from a position to another position is independent of the path. So we can choose arbitrary path or this path, any path. It does not depend at all on the path. It does depend on the starting and end point. All right. Let's consider the case, the conservative force does work, but the contribution is independent of path. That's quite important. Conversely, if f is conservative, then the line integral f is independent of the path. Okay. All right. Problem 14 to 19. For a path-independent force field F, that is conservative force, there is a time-independent scalar field U, such that F equals minus gradient U. All right, let's see. The potential energy is defined in this way. Why don't we compute the minus gradient U? If I take the minus gradient U, and U is here, so minus becomes this plus sign, and gradient. Gradient of this integral should be force. This is what we want to show. Minus gradient of potential energy is the force. Let's consider the change in the potential energy along the path along this x2 and x3 are fixed, and then just to shift the amount of delta x, shift the x1 component by delta x1. If it is finite, then we can make use of the Taylor's series expansion to find that the leading piece of this after subtraction, leading piece is a partial derivative with respect to x1 multiplied by delta x1. And second order piece is 1/2 second order partial x1 derivative of potential energy and multiplied by delta x1 squared, and so on. If we want to compute the potential energy explicitly, it does not depend on the path. So, for example, let me compute this integral by choosing an explicit path. This is origin. The starting point is the origin. Here we have put the reference value for the potential energy to be 0 at the origin. So from the origin to the point which has 3 components, x1, x2, and x3, let me first choose the path from 0 along the x1 axis, and then change the value of x2 from 0 to x2, and change the value of x3 from 0 to x3. to find out this x1, x2, x3 value. That one can be done by parameterizing x1 and x2 and x3 like this. On the path 1, all the values for x2 and x3 are 0, 0, 0. And the only variation is on the value of x1. And value of x1 runs from 0 to x1. Okay? In that case, dx1 equals dt and dx2 equals dx3 equals 0. So along the path, only one f1 dx1 integral survives, and remaining two pieces vanishes. If I choose, next we consider this. In this case, now value of x1 is fixed to be x1. And then value of y value, x2 value, runs from 0 to x2. So this is x1, t, and still this is on the xy plane. So value of x3 is 0. So among these integrals, dx2 equals dt, and t runs from 0 to x2, and these two values are fixed. Thus we have dx1 equals dx3 equals 0. Finally, on this path, x1 and x2 are fixed to be x1 and x2, but x3 value runs from 0 to 3. This shows that dx3 equals dt and dx1 equals dx2 equals 0. Okay. Let us review what we learned today until now. The work is defined by the integral, displacement integral for the force, scalar product of force and displacement. Time rate of work was defined to be the power, and kinetic energy is the explicit energy of a particle. And total time derivative can be computed with partial time derivative and chain rule that depends on the kinematic variables such as position or momentum. In this case, kinetic energy is explicit function of P, so total time derivative can be made. This one is vanishing, and first take the partial derivative with respect to momentum, and time derivative of momentum is multiplied. As we have seen, the time derivative of kinetic energy is the power, and that directly derives the work kinetic energy theorem, that work reveals the change of the kinetic energy. And we have found that conservative force does not work along a closed path. That results in the fact that the work from a position to another position is independent of path. And by making use of this, we can define a potential energy of a particle that depends only on point. That's it. Okay. We consider some examples of potential energy. Consider the spring force F equals minus kx. Potential energy with potential energy function of x, and you choose reference point, and from the reference point to a certain point f dot dx. This is one dimension, so just f dx. We substitute this one. It becomes a plus kx dx. And this is u of x0 plus 1f k x squared minus x0 squared. Okay. Simplest form is 1/2 kx squared plus u of x minus kx0 squared. It's x0. So this is arbitrary. So if we set ux0 equals 1/2 kx0 squared, then it is just they cancel exactly. So the choice of this u of x0 to be 1/2 kx0 squared, then we have kx squared. And wait a second. Let's go back to problem 14 to 19. For path-independent force field F, there is a time-independent scalar field U such that F equals minus a gradient U. So let us evaluate the integral explicitly. Let the coordinates of the 2 points be, origin is 0, 0, 0, and A is x1, x2, x3. Then the quantity U, x1, x2, x3 can be defined as, here we have reference value for the potential energy to be 0. So it is just integral from 0, 0, 0 to x1, x2, x3. Alright, let us evaluate this integral. This integral is composed of 3 pieces. F dot dx is f dot dx1, f2 dot dx2, f3 dot dx3. Okay? First one, 0, 0, 0 to x1, x2, x3. So there are many paths. So we want to compute the change in the potential energy. Change in potential energy, right? Just we evaluate the integral. Change in potential energy from this point to that point can be made. Alright, change in potential energy in here. You have x1, x2, x3, and we have delta x1 and x2, x3. And actually this is a change in the scalar field, and actually this one can be expanded in the Taylor series expansion. That is x1 is a partial derivative, right? And multiplied by delta x1 plus 2 factorial. x1 is the second order partial derivative of u, delta x1 squared, and so forth. As delta x1 goes to 0, the leading piece, this one will contribute dominantly, and remaining piece vanishes absolutely. So what we want to do is evaluate this integral using right-hand side. That means from x1, x2, x3 to x1 plus delta x1, x2, x3. f1 dx1 plus f2 dx2 plus f3 dx3. Alright. Here we state that here only the first term, this is the first term, survives on the right hand side because the ranges for the integrals over x2 and x3 vanish, because here this integral involves f2 dx2 from x2 to x2. Here integral of x from x3 f3 dx3. So this starting point and end point, they are the same, so it vanishes. Right? Therefore, we have only a single term, f1 dx1 style. Here, the differential with x2 and x2 are fixed, x3 are fixed. If we let this value very small, then we can find this is f1 x1 plus delta x1 subtracted by f x1. Am I right? No. No. This one is very small, so this one becomes almost constant. Almost constant. So it is about x1 plus 1/2 delta x1 multiplied by the difference, delta x1. and left hand side is u x plus delta x1, x2, x3 subtracted by x1, x2, and x3. Therefore, f1 is left hand side minus delta x1 u x1 plus delta x1 x2 x3 subtracted by xu1 x1 x2 x3. This is, and take the limit delta x1 goes to 0, then you will find that take the limit delta x1 goes to 0. This one is x1 plus 1 half delta x1. Therefore, we have f1 is this. In a similar manner, we can check that the f2 and f3 are all those values. If I combine everything all together, then you'll find F equals minus gradient of potential energy. Alright. Let us return to this problem. The curl of gradient phi, equals EI hat epsilon ijk derivative and derivative phi. And we have symmetry under exchange of J and K, anti-symmetric under exchange of J and K. Therefore, this one is exactly 0. F is irrotational. For example, central force. Central force is, for example, this F equals F of R, ER. That means X vector over R, F of R. Let me simply write it as X times F of R, where F of R equals small f of R over R. Alright, let us check if it is irrotational. The curl F, EI hat epsilon ijk, this force, sorry, let me write it F why because F is not good. F left hand side is F. Alright, or phi, scalar field phi, that's good. Round xj, round xk phi. Alright, then I can take the derivative, first one, and multiply phi. This way. here this one is delta JK. If it is JK, then this is symmetric on the exchange of J and K, and this is anti-symmetric under exchange of J and K. Thus, this guy is vanishing. Next, this one is EI hat, EIJK, XK. This one is a function of R only. So, and we take the derivative with respect to J of R. And again, we know that this is Xj over R. If we substitute this one, 1 over R EI hat epsilon ijk xk xj. Again, this is symmetric on the exchange of J and K, and this is anti-symmetric on the exchange of J and K. Therefore, this is vanishing too. This shows that the central force is irrotational. Alright, so for any conservative force, work from A to B is making the difference in the kinetic energy, that is the final state B, kinetic energy at B subtracted by kinetic energy of the starting point. And the work from A to B is the potential energy difference up to over negative sign. Because of this, because they are the same, kinetic energy and potential energy sum, that is a total mechanical energy, that should be independent of position. The sum of kinetic energy and the potential energy is called the total mechanical energy. Again, I say the total mechanical energy is defined for the case the potential energy exists, and we use the potential energy for the conservative force. Let us consider the potential energy that depends both on the position and time. That's quite complicated, which has an explicit time dependence. So, partial time derivative of the potential energy, just suppose, is non-zero. Let's see what happens. If it is the case, the potential energy is a function of both x and t, so total time derivative of the potential energy is a partial time derivative of potential energy plus it has an x dependence, and applying the chain rule, we multiply xi dot. In a similar manner, the kinetic energy's total time derivative is partial time derivative of kinetic energy plus kinetic energy depends on pi dot. But we know that this one is vanishing because the kinetic energy of a single particle is 1/2 mv squared or pi squared or 2m pi squared over 2m. Alright, so this one is u dot and t dot. T dot, of course, This is F times V, and U dot is partial time derivative and velocity dot gradient U, right? So if I sum these two, total mechanical energy, time derivative is time derivative of the kinetic energy plus time derivative potential energy, and that is plus V gradient U. But we know that F equals minus gradient U, right? Therefore, if I substitute in here, it is E dot is simply time derivative of potential energy. So if as long as the potential energy is has the non-vanishing explicit time dependence, the total mechanical energy does not conserve. So total mechanical energy is conserved if this one is zero. All right. So let's review what we have done this day. We began with the definition of work. Work is force, scalar product with the force and displacement integrated one. From this, time rate of work was defined to be the power, and power was a force, scalar product of force and velocity. Kinetic energy, non-relativistic kinetic energy of a particle was defined to 1/2 mv squared, that is p squared over 2m. Total time derivative of a function is a sum of partial time derivative, and in case of the kinetic energy, it depends on pi. So partial derivative with respect to pi and time derivative of pi. If it is also a function of x, and we add one more piece, x partial derivative with respect to xi and xi velocity. We verified, we calculated the work to find that the work changes the kinetic energy. That is called the work kinetic energy theorem. Work done by a force from A to B changes the kinetic energy, so that the final kinetic energy subtracted by the initial kinetic energy will be the same as the work during the process. The force was called conservative if the work done along a closed path becomes zero. Once the force is conservative, the work from point A to point B is defined independently of the path. And only the point dependent that function is called the potential energy. That is the work done by the force from a reference point to an explicit point given, up to over psi. The conservative force becomes independent of path, and this is our proof based on the fact that the closed path work vanishes. In addition, once the potential energy is unknown, we can compute the force by computing the minus gradient of that potential energy. All right, that's it for today.